everyone, I will be solving problem 2.22 from Introduction to Electrodynamics by Griffiths. The problem states to find the potential a distance s from an infinitely long straight wire that carries a uniform line charge lambda. Compute the gradient of your potential and check that it yields the correct field. One way of finding the electric potential in this problem is we can first find the electric field produced by the wire, and then we can take the negative path integral to find the electric potential. So let's first picture the long straight wire. And we can use the Gauss's law. So integral over the closed surface of E dot dA will be equal to the charge enclosed by the Gaussian surface over epsilon naught. And in this problem, because we have an infinitely long straight wire, we can actually use cylindrical symmetry to solve for the electric field. In order to use this, we need to draw a coaxial cylinder around the wire. Alright, so let's call the length of the cylinder L and the radius S. First, let's look at the sides of this cylinder and let's draw the dA component. So if we can draw a dA component right here, which will be parallel to the wire, as we can see. And now, due to symmetry, the electric field produced by this wire will be outward. And it will look something like this. Maybe going up. Alright, so the issue with this is that these two are perpendicular, and so will be every point in this whole surface and in this whole surface. So because we're taking the dot product and they're perpendicular, the electric flux from these two surfaces will be equal to 0. So we won't contribute to the total electric field, and we only worry about the long side of the cylinder. So to find the electric field, we can pick, let's first imagine two small elements, infinitesimal elements of charge, and we can call them dq1, we can call it dq2, and let's imagine a point on this surface over here. And what happens? So dq's, the dq's, boom, 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 there will be an electric field that looks like that, and the same for this one, the same for the bottom too. So this is from dq1, this is from dq2, this is from dq1, and this is from dq2. And we can see that these 2 points have horizontal components that end up canceling out because they're opposite and equal, and because these 2 points have been symmetrically picked. And the opposite will happen with the vertical components, because they are both going vertically up, or I should say vertically out from the wire. And the electric field ends up looking like this. Like that. And as I said, it goes out away from the wire in the S hat direction, and that is for both of these points. And the infinitesimal surface patch will be pointing outward as well, dA. So since they're parallel, we can get rid of the dot product and change, oh my gosh, and change this integral. Okay, so we took out the E field of the integral because due to symmetry, that E field will be constant along the whole Gaussian surface. And now to find out what area we're integrating over, we can unfold this cylinder. As previously mentioned, this cylinder has the length of L, and the sides will be the circumference of the cylinder, which equals to 2 pi s. And once we plug that in the equation, we are left with E, the magnitude. To find the charge enclosed by the Gaussian surface, we can look at our infinitesimal elements of charge that I drew already, and we are told that the wire carries a line charge of lambda. And it's uniform. So at this point, there's lambda. At this point, there's lambda. The whole wire has lambda. So the charge enclosed will be the line charge lambda, and then we can multiply that by the length of the Gaussian surface. L's cancel out, and we can solve for the electric field. And as we mentioned before, it is in the S hat direction. And now we can find the electric potential with the equation of the negative path integral from a reference point to the point S. Okay, so in a different scenario, our reference point could easily be infinity. However, we are told that this is an infinitely long straight wire and it carries a uniform line charge. So infinity cannot be the reference point since it would make our potential diverge. So we can easily pick another point and we can call it A. So in our diagram, we can just say A is found right here and then S is right here. And we need a DL element, so a length element. So it would be a very tiny element of length. And from A to S, we are going in the S hat direction. And it would simply be ds. So this is equal to dl. So when we plug in our electric field and our dl, it would give us we can take out the constants and then the s hats become 1, so we are only integrating over 1 over s. This is a very simple integral, so we are left with this. Okay, so now we do need to compute the gradient of this potential to double check that we found the correct field. this is the relationship between the electric potential and the electric field when we have the electric potential. Our the operator in cylindrical coordinates looks like this. Our potential only has an S in it. Therefore, it has no dependence on phi or z. So these would basically be 0 since there's no dependence on those. So when we apply the gradient, when we find the gradient, we're basically doing the partial derivative with respect to s of v. So we can take out the constant, and we can also rewrite the natural log of s over a. Oh, I forgot. So negatives go away. This format helps us visualize that because the natural log of a has no s dependence, it's treated as a constant. So when we apply the partial derivative with respect to s, it just goes away. So we're only taking the the derivative of the natural log of s. All right, so our final answer yields lambda over 2 pi epsilon naught s. And we actually got that answer here on top. So we have correctly found the potential, and we confirmed by taking its gradient, and our electric fields do match. Okay, and that's all. Thank you so much.